Okay, so in today's lesson, we're going to talk about convection and how it relates to the weather we observe at Earth's surface. So, weather can mean a lot of things, and we'll talk more about it later. But basically, you can think of it as basically wind and precipitation. Those are the two things we generally think of when we think of weather. How hard is the wind blowing? How much is it raining? Is it snowing? Is it sunny? And so on. And these all come down to this concept of convection, which I don't know to what extent you've studied it in the past, but let's just go ahead and get on it. So basically, what happens is this: the energy that drives weather comes to us from the sun. Basically, everything on Earth, except for the motion of continents, is pretty much powered by energy from the sun. And that energy comes to us in the form of light. And as we studied in the last lesson, most of the light is able to pass through the atmosphere with the exception of X rays, which is not much of coming out of the sun, but there's some, and ultraviolet light, most of which gets absorbed in the uh, um, thermosphere and stratosphere. However, the visible portion of it, the part that our eyes perceive and the part that we don't see, which is infrared light, that's the majority of the energy coming to us from the sun. Well, that passes through all the layers of the atmosphere right down to the ground. And when it hits the ground, most of it gets absorbed by the ground. Now remember, we can't create or destroy energy. So if energy comes in the form of sunlight and it then gets absorbed by the ground now has that energy. Well, how does that energy manifest itself? It manifests itself as thermal energy, heat. The ground gets hotter. So the sunlight transfers energy to the ground, and the atoms in the ground start shaking faster as a result of that. Now, what happens is any air molecule that's near the ground is going to, when it touches the ground, if I have a slow air molecule and a fast moving ground molecule, that fast moving ground molecule hits it, it causes the molecule in the air to shake more violently. So basically, and remember, you can't create or destroy energy. So the ground loses some heat and transfer it to the air. Now, the air we're talking about is this very, very, very like millimeter thin layer right next to the ground that's touching the atoms on the surface of the ground. Because remember, that sunlight passes through the atmosphere. It does not transfer energy to the atmosphere except the ultraviolet light. Uh, but when it hits the ground, it gives its energy to the ground, which then gives it to this thin layer of air. Now, that air, as it heats up, the atoms push each other apart, and that makes them less dense. And this is important because that's going to drive this concept called convection, which is an all important concept in many aspects of how our world works. So, as I said, when you heat the ground, it becomes less dense. Things that are less dense float upwards, like a hot air balloon. Hot air balloons float upwards because the air inside them is hotter than the surroundings. They expand, the hot molecules expand. That makes them less dense, and things that are less dense float in fluids that are more dense. And so this air, just like a hot air balloon, by becoming becoming hot from touching the ground and therefore less dense than the air around it, it floats upward. Now, basically what drives the weather systems, the fact that the wind blows in some places, for instance, has to do with the fact that this heating of the ground is not even. There are places where more of the energy is going to be converted to heat than others. For example, when sunlight hits the ocean, water has a very high specific heat capacity. It's very difficult to change the temperature of water. So the water stays pretty much the same temperature it was before the sun shined on. I mean, it changes a little bit. It does absorb energy, but it's really hard. The same amount of energy hitting water doesn't change temperature much. Same amount of energy hitting sand or any part of land changes it a lot. So we get this uneven heating. Now what happens is this produces it causes air to move upwards, and as the air moves upwards, because it's less dense, as it moves up, it does work. It basically pushes air molecules away from itself, and that causes its internal energy to drop, which means it's going to get cold. So as the air moves up, it then gets cold, and because it's now colder than the air that was around it, because it was essentially thrown higher than it belonged, it then falls back to the ground, and we establish this circular pattern of movement like this. And you've seen this in pots of boiling water, you've seen this in campfires, if you've seen a campfire. It's a fairly common phenomenon in many aspects of nature, and we refer to it as a convection current. So this circular motion of hot material rising and cold material falling in a gravitational field is known as convection. And it does a lot of things in this universe of ours, but we're just going to look today at what it does to weather. So, this upward movement of hot and downward movement of cold creates this circular region, say here, and we call it a convection cell. Well, now here's the thing: air, as this air moves up, there's less air here now, and so other air has to come and take its place. So this air moves in to take its place, but when it does, it gets heated and moves up, and this air gets cooled and falls down, and we have air in motion. Well, when air is moving, you and I, we call that wind. The weird thing is, anytime you've ever felt wind, that is because air is rising. Heated air is rising somewhere on the planet. It may not be here in Seoul, but somewhere not too far away, probably, air is rising and other air is moving in to take its place. So at the ground level, what we experience as wind is simply a consequence of hot air rising in one place and falling in another place, what we call convection. Now notice, here's an example of uneven heating. The ocean is colder, the land is warmer, and so that's going to establish a cell where it's just going to keep doing this as long as the ground continues to be warm. I like this diagram because what we see is, see how the sail is tipped in the direction the wind is blowing, and the smoke, don't ask me why they've got a fire going, but it works. The chimney smoke is being blown this way. And not that you need to know this, but we call this a sea breeze, that this cold air is moving off the ocean, getting heated and then rising. Now, the night comes. Now, what happens is it's hard to change the temperature of water. And it did get a little bit warmer during the day, but what happens is the land got really hot during the day, but then the land cools off a lot at night. Now we find that the water is warmer than the land. So now hot air rises here and sinks here, and I have a convection cell going the other way now, and you see that the wind is now blowing out to sea, and we call this a land breeze, and it's blowing off the land into the ocean. And I like it because you see the boat and the smoke tipping the other way. So this is an example of what we call convection. And convection is going to drive everything from examples like this to things like forest fires, thunderstorms, and hurricanes, and the movement of continents. So it's an important idea to grasp, but fortunately it's a pretty straightforward idea to grasp. Now, here's what makes weather. Weather is more than just the wind blowing, it's also precipitation. So let's think what happens. As this air moves across the water, it's going to pick up air molecules because of evaporation. Air molecules at the surface of the water are going to get ejected upwards because of the violent shaking of the molecules of the water. Sometimes throw them into the air, we call it evaporation. The air here is moist. As it moves over the land and heats up, that it moves upwards. But if you recall, as it moves upwards, it cools down. Well, if you cool down air that has a lot of water in it, that water is going to condense and form these little droplets that we call a cloud. So what we find is anytime air is rising, warm air is rising, as it cools, clouds form. So they form at a certain height. And this is the height at which the temperature of this rising air has dropped enough to reach what we call the dew point. It's a temperature and pressure in which the water is no longer able to remain as a vapor state. It condenses into a liquid state as little tiny droplets. Now what we find then is clouds form over the land during the day because of convection, and at night these clouds form offshore because that's where the air is rising. But the point is, rising air carries with it moisture, and that moisture then condenses, and if it condenses enough, it leads to precipitation. So it is this convection that allows for there to be life on land, because otherwise there wouldn't be any rain. Rain is driven by this process of convection. It wouldn't rain if air wasn't being lifted upwards and cooling down and causing the condensation, and the water over the ocean wouldn't be driven onto the land in the first place. There wouldn't be wind moving it if there wasn't this uneven heating causing the formation of these convection cells. Pretty powerful, right? Now, if you recall from our last lesson, we said almost all of the moisture in the world and all of the weather, all of the wind, all the precipitation happens in the troposphere. Basically, what forms the boundary between the troposphere and the stratosphere? Well, that barrier between what we call the tropopause, that's essentially the maximum height that convection is able to lift things to. So when you heat the ground surface and it causes air to rise up, the highest it will go is evidenced by what's called a thunderhead, a cumulonimbus cloud, and those get right up to the tropopause. The only convection that I'm aware of that has gone beyond that, at least in human history, is hydrogen bomb explosions have pushed the convection caused by those has moved all the way up into the stratosphere, which caused problems because it drifted all over the planet. But the point is, heating from the sun only causes enough convection to lift moisture this high before it falls down. And so that is why the troposphere is as deep as it is, basically 10 kilometers deep-ish. And that's because that's how high convection can be lifted. Now, let's talk about pressure, because air pressure is going to be an important concept here. So the more molecules you pack into a space, generally speaking, if you kept the temperature constant, the more molecules you pack in, the higher the pressure is going to be. Think about a basketball. The basketball doesn't have much pressure, or a car. It doesn't have much pressure. How do you increase the pressure in a ball or a car tire? You add molecules into it. You cram molecules closer together, and the pressure goes up. All right. Now, if you take molecules out of the tire, take molecules out of the bar, the pressure goes down. So the idea is more atoms crammed together, more pressure. Fewer atoms crammed together, less pressure. Well, let's think about this. The sun heats the ground, and it causes air to move upwards. Well, if air leaves here, then there's less air here, and less air means less pressure. So we end up with low pressure at the surface of the Earth, where air is rising due to convection. Now, let's not worry about the upper part here. Let's just follow it around. It goes up, it cools down, and now it's falling to the ground. Well, now here's some air, and more air is falling into that same spot. Well, if you add air to more air, what's going to happen is the pressure is going to go up. Your pack it's like you pushing air into a tire, essentially. And so this falling air is going to increase the pressure here. Okay? Rising air, low pressure. Falling air, high pressure. Now, rising air, low pressure, remember, also makes clouds. So we associate low pressure with clouds and rain. And that's because low pressure is forming where convection is lifting atmospheric gases upward, and the evaporated water that's in them is going to come out as clouds or precipitation. And we associate high pressure with dry air, because as this goes up, it loses its moisture as precipitation over here. And now this air, as it gets over here, has been essentially dried out, like squeezing a sponge. And so the air that's coming down is dry air. So we associate high pressure with clear weather, no clouds, and dry, high and dry. Okay. Now, all right. So that's the idea then behind pressure and its role in convection and weather. The thing is, air always moves, like any fluid is going to move from areas of high pressure to area of low pressure. The molecules get pushed from high pressure. Well, I guess in this case, I got to point the other way. They get pushed from high pressure to low pressure. So the pressure is high here is going to push atoms this way. All right, and so that's what makes our breeze. So wind is just a consequence of differences in pressure, and these differences in pressure are in turn driven by this convection process. Now, thunderclouds are a particularly spectacular and very graphically informative illustration of this process. Thunderclouds are formed by very rapid, powerful convection. They tend to happen in the warm seasons when solar radiation heats the ground considerably, and you get strong and prolonged convection that keeps pushing the air higher and higher and higher, pushing it far beyond as where it would normally rise if it wasn't so strong, all the way up to the top of to the bottom of the stratosphere, the top of the troposphere. And you can see that this thing here is sometimes called an anvil. So the top of these clouds, they tend to flatten out when they reach the stratosphere, or at least the tropopause. So these things are really amazing. You can see them from the bottom going all the way up. The reason it's so dark underneath these thunderstorms is because light can't penetrate it. The reason it's cold, if you've ever been in a thunderstorm, the air gets very cold right before the thunderstorm happens, because you have air falling from all the way up, basically at the boundary with the stratosphere. And as it falls down, it accelerates quite a lot. And so just like a rock falling from a very high place is going to end up going very fast, air falling from a very high place is going to be going very fast. So thunderstorms are associated with very powerful winds. And also what happens sometimes is you get particles that keep circulating within here. There's very strong convection in here. And at the top here, it's very, very cold. It's so cold that the water is going to be frozen. And so what happens is we have ice particles, at least in the upper parts of these clouds. And as these ice particles move past each other, friction separates the charges, and that's what leads to lightning. These electrical discharges are a consequence of the convection within these clouds that brings frozen droplets in contact with other frozen droplets, and that friction causes the formation of the charges that lead to these lightning strikes. So here's a nice graphic that basically shows this here. So basically, the dropping of the temperature of air with height is known as adiabatic or adiabatic cooling. Okay, and so just think if you had still air and you had an escalator and you just started moving up this escalator, what you would notice is it gets colder and colder and colder at a very consistent rate as you move upwards, and that consistent rate is about 7 degrees C per kilometer of altitude. And so what happens is, as you get higher and higher and higher, it gets colder and colder and colder. And you can see by the time you get to about 4 kilometers up, it's going to be frozen. That's why mountains higher than 4 kilometers, they have snow at the top all year. Why? Because it's too cold for it to melt. And the higher you go, the colder it's going to get. And what we find is that these thunderstorms carry moisture all the way up here. Like, look, from this point up, it's frozen. So that's why up here we get these ice particles that lead to the formation of electrical charges that then cause lightning. The last thing I want to say about this has to do with adiabatic cooling, but not convection. But at least like convection is involved because there's wind involved. But hear me out here. I'm sorry for all the text here. I'll give you a graphic on the next page. But the idea is this, that there are places on our planet that you're going to investigate next time we meet, where when wind is blowing, if it blows in a very consistent way, day in and day out, we call that a prevailing wind. And there's many places on this planet that have prevailing winds. The wind in certain places always blows in the same direction with very few exceptions. Now what happens is if that prevailing wind happens to hit a mountain range, so what happens is the wind is going this way. Well, if the wind just went this way and there's nothing to hit, well, it just move. If it doesn't go up, it's not going to precipitate. It's just going to carry this moisture until it goes up. But what can make it go up is a mountain in its path. Let's see, I got to get my mountain anyway. So now, if this air is coming in and it hits a mountain, that prevailing wind is going to push this air up the mountain. And remember, as air moves up mountains, adiabatic cooling is going to cool it about 7 degrees Celsius per kilometer of height. Well, turns out many mountains are such that not only does the air just hit it, it tends to hit it and move up like this, right? And so as it moves up, it often cools enough to cause clouds and precipitation to form on the side on the side where the wind is hitting. But what happens is, as it goes up this way, it cools and it condenses and it causes precipitation, and then it loses all of its moisture. And as it comes over the other side, it no longer has any moisture, and it's very, very dry air. And that dry air then causes a drying of the ground around it, and that leads to the formation of deserts or grasslands immediately on the downwind, or what we call leeward side of the mountains. And so we find is there are many places on the planet, I'm going to have you search for these, where you see on one side of a mountain, rainforest. A kilometer away from it, desert. It's like a really weird, stark contrast that we get. And this is caused by adiabatic cooling and this whole process. So this is like, you could call it like forced convection, that we're forcing the air up because of a mountain being in its path. So here's an example that shows it. So I have prevailing wind coming off the ocean, picking up all this moisture. If this mountain wasn't here, it would just move inwards and it wouldn't precipitate. But what happens is there's a mountain in its path, so the air gets pushed upwards. As it moves upwards, adiabatic cooling cools it down, and it begins to condense and then precipitate. So we get a rainforest, or at least a forest, quite a bit of precipitation here, but often rainforest. And then what happens is by the time it gets to here, it's lost all the moisture it's got. So now the air coming down the other side is dry, and as it moves down, it gets even drier. So on this side here, we end up having a desert or a scrubland or something like that. Let me give you an example one. This is from my part of the world. I come from the Pacific Northwest of the United States, and we definitely see them there. So look at this. This is near where my brother lives. This is Mount Hood. Unfortunately, this is right now, it's just all on fire. It's terrible what's happening there. But basically, the Pacific Ocean is over here, and as that air from the Pacific Ocean comes in, it gets forced over this range of mountains here called the Cascades, and as it does, it just dumps rain here. And there are rainforests, like what are known as temperate rainforests, rather than tropical rainforests. Temperate rainforests happen here, but by the time it crosses the crest of the mountain, which is right here, this is the highest point of the mountain, it comes down the other side and it's completely dry. And we have this very dry desert area on the just on the opposite side of the Cascade Mountain crest here. So we see these rain shadows all over the place, and they're kind of fascinating. I'm going to have you do an investigation of them using Google Earth here next time we meet. Okay, so that's got it for convection, weather, and all the associated things with it. Yeah, see you later, guys.